If I handed you a laptop and I asked you to explain music to it, you'd probably question my sanity and then ask which drugs I'm on. Well, that's exactly the problem I've been working on. Not the drug part, that's fine. The music part. Wait, let me explain. You see, aside from the occasional video I put out, I also write music. A lot of music. In fact, every single piece of music you've ever heard in my videos was written by me. Not because I'm trying to prove anything, but because I love the process. You see, I'm one of those guys who would hear a bird chirping and immediately try to turn that into a synth. That's just how my brain works. But I'm also a tinkerer. I love pulling systems apart and figuring out what makes them tick. I wouldn't have put out a whole video on building a voice-activated assistant if I didn't. So I've always lived right at the intersection of two worlds, the creative side and the technical side, and this project sits exactly in the middle. But before we talk about computers, we need to start with something simpler. What even is sound? Now, we've all heard the physics explanation, that sound is just vibrations, waves moving through the air that your ears pick up and your brain interprets. And that's true, but it's not very useful, because that's not how we actually experience sound. When music hits your brain, you don't think about waveforms or frequencies, you think in meaning. You recognize pitch, you feel rhythm. Your brain immediately starts categorizing what it's hearing. Let me show you what I mean. Take a listen to this. When you hear this, what do you actually notice first? Most people don't immediately think about genre. They notice structure. You can hear that it's an arpeggio. And if you know some music theory, you'll probably recognize that it's in C minor. Even if you don't, your brain still understands that these notes belong together, that there is some kind of tonal center. Now, from a rhythmic perspective, it's sitting at right around 128 BPM. I don't even need to add a backing track for that. Your brain is already filling in the space and locking into the pulse. But I'll add one here just to make it obvious. What else can we hear? Well, it's rising, so it has a general direction, and it's playing 8 notes. Those are the objective properties of the sound, the notation. Now let's take that exact same ARP and place it in a few different contexts, like trap, or synthwave, or even EDM. Nothing about the ARP itself has changed. What changed, however, was everything around it, the context it lives in. That context is what we usually think of as genre. But that's not really what I'm interested in teaching. What I care about are the parts that don't change, the building blocks of sound that stay consistent no matter where you place them. Those are audio samples. For anyone outside the producer world, audio samples are basically the raw ingredients of modern music production. They're snippets of sound, synths, textures, field recordings, anything that can be captured and reused. They're where ideas come from. They're how tracks get started, and entire genres of music were built around sampling. That's the space I'm operating in. But so far, we've only talked about structure, notes, rhythm, and timing. There's another layer we haven't touched yet, because two sounds can play the exact same notes at the exact same tempo and yet still feel completely different. And that difference comes down to timbre, how sound actually feels. So let's go back to that same ARP. Structurally, nothing has changed. Same notes, same rhythm, same timing. But now let's listen a little closer to how it sounds. You can hear that it lives in the mid-range of the frequency spectrum. We can call it bright, a bit airy. There's a sharp attack, so it feels like a pluck. And there's a good amount of reverb giving it some space. Those aren't genres. Those are tonal characteristics. Now, let me change just the sound, not the notes. Same ARP, same timing. But suddenly it feels brighter, sharper, more metallic. Now, thinner, wider, more atmospheric. Nothing about the musical structure has changed, only the timbre did. So, this is where things start to get interesting. Because timbre is the layer that gives a sound its personality, it's what makes a note feel soft or sharp, warm or cold, natural or synthetic. And it's also the part that's hardest to describe with words, even though producers do it every day. When they search for sounds, they're not thinking about C minor ARP. They're thinking about tone, brightness, darkness, how distorted it is. That shared vocabulary, even when it's subjective, is what lets producers communicate sound. And it's exactly the layer most systems struggle with. And that separation, structure versus timbre, is the core problem I've been trying to formalize. Essentially the science of sound. Because I realized something pretty quickly. If I want a computer to actually understand music, I can't just show it sounds. I have to actually teach it these distinctions explicitly. Now, at this point, some of you are probably already thinking, okay, now this guy's gonna try and say how he fed a bunch of stolen music to an AI. And I need to stop you right there. That's not what I did. I didn't scrape music catalogs, I didn't pull in other producers' samples, and I didn't try to shortcut this by feeding a machine to other people's work and then just hoping it figures it out. It doesn't even really work like that. But I'll get to that in a moment. What matters here is that I'm a musician first. I've been writing music since I was a teenager, so this was never about replacing that process. The goal was always to augment it, to open up new ways to explore ideas and find inspiration. Whether that inspiration comes from recording a passing car or abusing a reverb plugin. So instead of asking myself, how do I give the computer even more sounds? I asked a very different question. How do I formalize and teach a computer to listen the way producers do? And that's where the real work began. The first step was building a vocabulary, a way to describe structure and timbre that didn't contradict itself. Because before a model ever sees sound, it has to understand the language you're using to describe it. And that's why the idea of just throwing a pile of samples at a computer and hoping it figures things out doesn't really work. The problem is, there isn't much producer-centered data out there that captures both musical structure and timbre in a consistent way. So I had to build it. Over months, I was creating and categorizing sound along two axes, timbre and musical structure. Just like what we did with that ARP earlier, but at scale and over hundreds of sound profiles. For example, this synth could be called bright, airy, sparkly, plucky, wide. Or, if we're talking about a flute, breathy, woody, soft, hollow. Or take this bass, round, warm, sine, thick, because the notes themselves are the musical backbone of the design. And that's the other axis. Things like a chord progression with a melody, a rising triplet, a 16th note bass line, an 8-note ARP pattern that falls. Those are the underlying notation that stays true even when the sound changes. And this all has to be defined methodically, because the model can't learn concepts from messy labels. If the vocabulary is inconsistent, the model just learns confusion. So the question becomes, how do I go from this to something a model can actually learn? And that's where I need to get a bit more technical. So here's a high-level look at how these systems actually learn. And don't worry, I'm going to keep this intuitive and not academic. Now, these systems don't store sounds, they store relationships. You can kind of think of it like a map. Not a 2D map like you're looking for buried treasure, more like an old sci-fi star chart. Except instead of stars, each point represents a musical idea. Brightness, rhythm, BPM, movement, texture. In machine learning, this kind of map is called an embedding. But it's important to understand it isn't learned all at once. As the system is exposed to sounds and the descriptions that go along with them, it gradually learns how those ideas relate, which concepts belong near each other and cluster together, and which ones don't and may be placed further away. And this isn't sound, it's not audio, there is no waveform here. It's more like a set of directions, a shared coordinate system that both the language side and the audio side can agree on. So maybe over here you get clusters of bright, airy, plucky concepts. And then over here you get darker, heavier, or more aggressive textures. Maybe timing information like 4/4 time or triplet time is kind of over in this region. Now, this is obviously an oversimplification. I am drawing this in 3 dimensions because that's all we can really visualize. In reality, the system is working in many dimensions at once. You can think of it as almost building multiple overlapping maps simultaneously, so it can move through the space in whatever direction it needs. But the important part is this: that space isn't the sound itself, it is a map that helps the model navigate towards the sound. So the next question is, if this is just the map, how does it actually make sound? Well, that starts here. That might sound familiar. It's the same kind of hiss you hear when a TV or radio isn't tuned to anything. This is essentially what the sound side of the model starts with, noise. Now, to be clear, it's not literally radio static, but it's the same kind of idea, random noise. That map we just talked about doesn't create sound in its own. What it does though is it guides how this sound gets shaped, step by step. The system nudges the sound in a particular direction, removing what doesn't belong, reinforcing what does, until what's left starts to sound intentional. So sound isn't pulled from a library, it isn't copied, it's carved out of the noise itself, from the concepts that I learned throughout training. Another way to visualize this is to think of it like a block of clay or limestone. You don't add the statue, you slowly remove the material bit by bit until the shape reveals itself. The map tells the system where to carve, and the noise is just the raw material. And the only way that works is if the map is clear and well constructed, where the relationships between the structure and timbre need to actually make sense. That's why the vocabulary mattered so much, and it's why this couldn't be done by just throwing samples at a machine. I had to be extremely methodical, making sure concepts overlapped where they should and stayed separate where they shouldn't. Take these two basses. One is a sustained respace that's warm with some slight distortion and reverb. The other is a thick pluck bass with some sub and reverb as well. On paper, you could just call them bass and move on. And yeah, the model can learn from that, but it won't learn nearly as well as it could because these two sounds are very different, even when they're playing the exact same notes. So instead of collapsing them all into a single label, it actually makes more sense to describe them with overlapping terms where they share characteristics and distinct terms where they don't. That way, the model learns both what they have in common and also makes them different. But this is also where things get tricky. Some sounds are genuinely hard to describe. Take these two audio examples. They're playing the exact same notes, they serve the exact same musical role, and a producer would probably recognize them as both a 303 or acid synth. They sound very different from each other. So, instead of forcing them to be identical, you can describe each one with its own specific timbral traits, and still include 303 as an overlapping concept, just like a human would. If you hear the similarity and the difference at the same time, the model can learn that too. So once that vocabulary was all in place and I paired it with all my audio, that's when the real fun began. I ran everything through a fine-tunable model called Stable Audio Open, letting it slowly practice, adjust, and refine that map we've been talking about. It was learning how structure and timbre relate over and over until it's stabilized. That's the important part. The AI isn't deciding what sounds cool. It's navigating through the space it was taught, using the same kind of cues producers already use. So, when I ask for something, I'm not asking for a song. I don't need an AI to finish a track for me. What I need is something that augments the process. What I'm really asking for is behavior. How should this sound move? How should it sit? How should it feel? What instrument am I even going for? And the output isn't a finished idea. It's a starting point, a sketch, a building block, something I can shape, layer, abuse with effects, or throw away entirely, just like any other sample. But now, instead of scrolling through folders or tossing random sounds into a track and hoping they fit, I can explore sound the same way I always have, just through a different interface. So, let me show you what that looks like in practice. And spoiler alert, you've already been hearing what it can generate throughout this video, and that's the point. The sample lives in the background, but the human is the one who takes it home. So, let's dive in. Since the model was trained not just on broad instrument categories, but also timbral characteristics, it lets me get a level of control I honestly haven't seen in open source yet. To put it through its paces, let's start small and work our way up. For consistency, everything you're about to hear is an F minor at 128 BPM, but it supports all 12 keys and a wide range of tempos. First prompt, piano chord progression, low reverb. Easy enough. So, here's what it gave me. Not bad. Now, let's make a tiny tweak. All I'm going to add is strummed. That's not an instrument. That's a playing style. Have a listen. Yeah, you can hear it. Same timbre profile, but the note articulation changes. So let's go a bit deeper. I'll add the words complex and melody, and bump the reverb from low to medium. And to give it a challenge, I'll add the words high distortion. Now, it hasn't seen any sort of audio with pianos that have distortion applied, but it should understand all these concepts and be able to figure out what that should sound like. This is what it came back with. So now we can hear that the terms complex and melody introduces more melodic movement, and that low reverb versus medium work. So it has an idea of space. It's also applied the distortion like an AI-based audio effect. That's what I mean by control. It understands melody, harmony, and timbre all at the same time. Alright, let's actually push it. I want a sine wave bass that's plucked. And let's bring complex back into the mix. Yeah, that's nice. Okay, here's a much harder one. Let's ask for a 303 acid synth lead with pitch bend that's warm, gritty, silky, along with both reverb and ping pong delay. Check this out. Wild. And the important thing to remember here is it's broken down these terms down to their core concepts and is reinterpreting them on the fly, which means you can run the same prompt again and again. It gets something totally different but coherent. And if we add just one more word, say triplets, it changes the melodic structure while still keeping that whole acidic 303 vibe intact. That's the separation between melody and timbre working together. Now, earlier I said I avoid a genre, and that's mostly true, but I did include two very narrow ones. Dubstep and chiptune. Dubstep sounds and particularly dubstep growls are very distinct. They're often created by sweeping comb filters across a frequency, and while they can be described that way, it makes way more sense just to call them growls, so instead that term actually helps narrow the sound instead of broadening it. For example, here's an output using the term dubstep and melody. Same thing with chiptune. That genre is defined by very specific limited waveforms, so it works more like a technical descriptor than a vibe. But here's the key part. The model doesn't just know what chiptune is. It actually understands the waveforms themselves, which means you can smoothly move from a prompt like chiptune chord progression sine wave to the exact same prompt, but with square wave. Or pulse wave. And everything in between. And that's where the real power is. Timbre mixing unlocks a ridiculous amount of creative space. For example, check out this electric bass acid formant vocal hybrid. That's absolutely something I could work with, and I know a lot of other producers could too. But we could do a lot more than just generate samples from scratch. Because the model understands these characteristics, you can also feed it existing audio and ask it to reinterpret it. Here's a simple guitar melody. Now, I'm going to ask the AI to just apply some vocal choir characteristics. You can see how powerful this can be in the right hands. Not only can you make an infinite amount of variations from the generative side, but you can now take your own audio recordings and ask the AI to put its own spin on it. I mean, I could sit here and show you examples all day, but I think the point is clear. This isn't about finishing songs, it's about better building blocks. And with that, I should probably also address the elephant in the room. Because when a lot of producers hear AI right now, they think of things like Suno and Udio, song generators trained on massive music catalogs built without consent and marketed as full replacements for the creative process. I get why people are angry. I'm angry too. That approach strip mines musicians' life's work and it turns years of craft into a prompt. That's not what I want music to become. And if that was the goal, I wouldn't have spent months formalizing timbre, structure, and musical behavior just to end up with a one-click song machine. I am a producer. I actually like making music. And sample generation, at least in the way I'm using it, isn't a replacement for the writing process. It's a creative spark, something you reach for when it fits. It's also not a replacement for synths or VSTs. A prompt or a sample can help you discover an idea, but it doesn't give you the same depth of control you get from a real instrument, a synth, or a sound you've shaped by hand. That control still matters. Taste still matters. So instead of building something that finishes tracks for you, I built something that stays out of the way. And yeah, I could lock this behind a paywall, sell access, play the same game most people are playing right now in the AI space. But that was never the point. I want this to be accessible. I want it to be ran locally. I want producers to explore sounds without subscriptions or lock-in. So to that end, this model is being released entirely for free. You'll find full download links in the description. I've optimized it to work on most desktops and laptops in a local Gradio interface I designed that runs entirely on your hardware. The interface will also give you all the MIDI that comes out of the sample. No subscriptions, no training on your outputs. Your sound stays yours. This is the kind of AI I actually wanted to exist, so I built it. And with that said, thank you for sticking with me all the way to the end. I hope you learned something along the way. If you think this could help another producer or someone who just finds this neat, feel free to share it. But until next time, bye.